All right, so I'm going to get started, and today I'm hoping that I will remember to pass the roll sheet around because I kept forgetting, and not only for this class, it's also for all of my other classes.
Can we call you Matt, the professor?
Absent-minded, yes.
Absent-minded.
The absent-minded professor, yes. Today is the 3rd, and I'm just going to cross out the column where, I forgot to pass it around.
It's like it never happened.
Yep, just like that. All right, so let me double check on the recorder. It is recording, so let's go ahead and get started. So I sent you guys an email, kind of talking about the grading of the multiple choice question, the test, homework assignment. So, that's kind of pretty much, all in the explanation itself. If you guys have any feedback, you can talk to me in person. You can send back, some email. That's all fine. If you want to talk about it in class, that's fine with me as well. Okay, but that kind of explains from my perspective why I do things the way it is done. Okay, so just to re-emphasize, why there are negative points associated with wrong answers. The only reason why they're there, why the negative points are there, is because for anyone, if I just go out there, drag someone into this class, to take that test or do the homework assignment, that person does not know a single thing about what we're doing here. That person is to get a 0, regardless of whether that person decides, oh, I'll just kind of leave everything blank and not turn in anything, which is one way to get a 0. Okay, if you don't turn in anything, that particular question does not score, and it does not get any points. It won't be negative at all. But if the other person, the person that does not know anything about discrete structure, decides to randomly guess everything, answer A, in all the questions, well, that person really should still get an 0, because the score reflects that that person does not know anything about the stuff that we have been talking about in this class. So the negative score of wrong answers is really just to balance out the chance factor when someone is randomly guessing. It is not designed to be punitive. It is not saying, oh, it is wrong to be wrong. That sentence has something wrong with it too. So it's not because of that. It's really just for balancing out the chance factor. When someone just decides to randomly guess, in this case, it will just be a flat 0, statistically speaking. Now, some people are consistently luckier, and some people are consistently unlucky compared to other people. So I cannot guarantee whether when you do a random guess on the questions, whether there'll be no bias to your score. But in general, statistically speaking, it has 0 bias to either side. So that said, what I did not mention in my email is if let's say you have 5 choices, okay, and you know that one of the answers is right in the 5 choices. So out of and you can only eliminate one choice and say this one is clearly not the answer. In that case, if you just randomly guess, chance is already leaning on your side. There's a bias to get a positive score for that particular question. Now, once again, I have to emphasize it is statistically speaking, because some people will say, but I tried it several times, and every single time I can eliminate 2 possible choices out of 5, and I always end up guessing the wrong one. I cannot say anything about it because it is all statistics. Okay, is that okay so far? Does everybody kind of understand what it is? Okay, so it also has to do with the grade assignment, the letter grade assignment scheme that I use in this class. If you remember, an F is centered around 0 points. So I really have to make sure that someone who does not know anything about the subject matter is going to get a 0, because that is where an F is centered. So that's another reason why the scoring is done that way. If you go to any type of college SAT exams, any type of exams like that, they use exactly the same way. They balance out the wrong answers with negative scores. So if someone does not know which one is the right answer, no clue whatsoever, the average is just going to be a 0. All right, so there is that.
So the sum of all correct answers is equal to the sum of all negative answers.
That is correct. Yep, that's basically it. Yep.
Yay, statistics.
Well, that's one part of statistics. But as I said, some people are consistently more lucky than others, and others not as lucky. The Moodle does one thing that's nice because it does not record a negative score for an entire exam. So if someone ends up with a negative score, for one particular exam, it is rounded up to a 0. I haven't seen that happen yet, but theoretically speaking, that can happen. All right, so we're still on functions and relations from last time, and I'm hoping most of you have a chance to at least get started with the function homework, which is in the form of a quiz, even though the due date is it on Thursday?
Tuesday.
Next Tuesday.
Yeah.
Yeah. So it's on next Tuesday, so that gives you a little bit more time to think about it, to read about it, and try to do your homework. So are there any questions related to your function homework? Yes?
I did not get an email from you, so I did not know if it was postponed. So I've already taken it.
Okay. You did not get an email from me?
I did not get your email. Or I haven't read it yet. Check last night.
We talked about it during the class last time. That was discussed, during class. And the reason why I did it was, I cannot even remember, but it was recorded, hopefully. Do you guys remember why I postponed it? Because it had not been opened. The entire section had not been opened because I made a mistake of you needed 100% of overall score for this class in order for this whole section to open up, which is kind of like a circular reasoning, because if I don't open it up, you guys cannot really study and you cannot get a 100% score. But because you cannot get a 100% score, you cannot read the material in order to get a 100% score. So I had to change that, and that was the reason why I postponed the quiz. So we can talk about it after class, but I'm just recapping, why I postponed the deadline and when it was done. But you also need to look into why. Are you still getting my email, like the one that I sent this morning?
I haven't checked since last night.
Okay. So you might want to check because you want to make sure that you are getting all the email messages from this class too. Okay. All right. So last time we talked about the composition of functions. Particularly, we talked about the inverse function and how you can use if a function can be decomposed into components, and each component has an inverse, you can combine the inverses of the components back into the inverse of the composite function. And last time I did a few illustrations. Okay, I showed a few examples of how this works, and that was the last topic on functions. Are there any questions regarding functions? With all the stuff that we have talked about, composition is one. We talked about what is injective. We talked about what is surjective. Bijective is easy because it is just injective and surjective. So are there any questions about functions up to the topic that we talked about on Thursday last week? No questions? Okay. If there are no questions, I do want to go through this slide here, which was not there until sometime last week. I think I worked on this last week. You can always check because the date is at the bottom here. So I did work on this last Thursday. And we'll go through this slide here. Okay, so the first part of application is, it allows us to express certain things. So it is at least, easy to express. Did I go through this last time? No? Okay. Okay, so the question is, how do we qualify an algorithm, a sorting algorithm, that it is getting its job done? Okay, I don't even care about the algorithm itself. Okay, you can use quick sort, you can use bubble sort, you can use selection sort, you can use merge sort, you can put all the elements into a magical box, and then you pull all the elements back out. The question is, how do I know whether that magical box is getting the job done or not? Okay, how do I describe the proper outcome of a sorting algorithm? That was the question. So what we do, or what I do here, is I define, a whole bunch of terms. So let's say the array that is being sorted in place is array A. So A bracket something are just elements of the array. And this is the initial state of the sorting algorithm. So this statement is really just saying for all I from 0 to n minus 1, where n is the size or the number of elements in the array, I'm just defining what k's are, what the constants are. So I'm just defining k of I is the initial value of element I of array A. That's all what this is saying. Okay, it is just defining what the constants k of I are for I going from 0 to n minus 1. Because I need to refer back to the initial value of elements in the array in order to express the correct answer after sorting. Are we still doing okay so far with this part? Okay. So this part is not really a proof of any kind. It's not a statement of any kind. It is just defining what is k of I. So the expression is down here. I'm pretty sure I talked about this last time, but let's go over that again. Okay, so this is the statement, and I'll break it up into parts. I think last time I did the same thing. So it says right here, okay, so it basically says, okay, if the outcome of a sorting algorithm is in fact getting the job done, of sorting, then we can find a function f, okay, that exists function f. It doesn't mean that a function f is unique, okay? It simply means that there exists at least one function f that can map from 0 to n minus 1 to 0 to n minus 1. So it may not be a unique solution. There can be multiple functions that have the same properties. But there should be at least one of these. And the qualities is f has to be bijective. In other words, it has to be injective and surjective at the same time. So let's go over bijective one more time, because I think some people may have forgotten what is injective and what is surjective, which you need in order to become bijective. Injective means for every element in the domain, they have to map to unique elements in the codomain. Okay? The other way to say that is no two elements of the domain can map to the same element in the codomain. Is that okay? Yep. Go ahead. Yep.
Does that mean that every element in the domain must be mapped to at least one element in the codomain?
Okay, in order for something to be called a function, every element in the domain must be mapped to one and only one element in the codomain.
Okay, so the answer to my question was yes.
Yes. Yep. But that's just injective. So injective means each element has to map to a unique element in the codomain. Surjective means all elements in the codomain need to be mapped. So you're not only going to use one or a few of the elements in the codomain, every single element in the codomain must be mapped. So bijective means it has to be both. It has to be injective, and it also has to be surjective. Now when you have bijective function, it also implies you will have an inverse. Okay? Given the outcome of a particular function, you can always apply the inverse function to find out what you can start with that function to get to the end result. Are we still doing okay so far with a quick review of injective, surjective, and bijective? Sort of okay? All right. I know this stuff is really boring because you cannot run the code in any way. There's no way to go through GDB to debug the code and visualize anything. But it is kind of important, okay? It is kind of important. Okay, so in this case, I should be able to find a function f that can map from 0 to n minus 1 to 0 to n minus 1. F has to be bijective, which means it is, it meets all the requirements that we just talked about. And the following also has to be true. Okay, and this is where I made a mistake earlier, on Thursday last week, and I fixed that during class. This is the first requirement, which has nothing to do with the function itself. This requirement simply states, after the algorithm is run, okay, that does the in-place sorting, for I being 0 to n minus 2, a bracket I, which is just an element in the array, has to be less than or equal to a bracket I plus 1, which is the element next to it. Okay, which is a basic requirement of having an array that is in order. Okay, but that does not mean this is the result of a correct sorting algorithm, because you can always meet this requirement by reinitializing every single element in the array to 0. That would easily meet this requirement, but your algorithm would not be a sorting algorithm. Is that okay so far? So this is only defining what is in order. Okay, this array is now in order, but not necessarily the result of a sorting algorithm. The other part is important because this part is saying we are only using exactly the same values as in the initial array before the sorting. Okay? Well, but that's easy to do too, because all you have to do is to pick the first element of the entire array and initialize the rest of the array with the value of the first element, and it will still meet the first requirement, which means it is in order, and the quote-unquote second requirement that it has to be a value coming from the initial state of the array. So this is why I have the function f. This is also why a function, the concept of a function, is useful. So let's take a look at this is what this is really saying. The first part that is important is now for this particular quantifier, I is no longer going from 0 to n minus 2. I is now going from 0 to n minus 1, which means it is applied to every single valid index in the array. And then the second thing is, assuming I is going from 0 to n minus 1, the a bracket I has to meet this requirement. A bracket I has to be equal to k, which is the constant that we defined earlier, but the subscript of k is no longer I, it is just f of I. In other words, there has to be a way to map the initial values of every element in the array to the final value of each element in the array. And it has to be a 1-to-1 correspondence. That's what it's saying. Are we still doing okay so far with this? I can draw you a picture, if the picture would help. So if you look at the initial values, okay, so let's say we have K1, K2, K3, K0, okay, because we start counting from 0. So let's say we're dealing with an array of 4 elements. And A bracket 0 used to be here, A square bracket 1 used to be K1, and so on, okay? And then we look at the final state of the entire algorithm. After the algorithm is all done, A bracket 0 still has a value of some kind. A bracket 1 has a value of some kind, A bracket 2, and then A bracket 3. So each element in the array has a final state, which is the value after the sorting algorithm is all done. So what this means is f, which is a function, which is a mapping, is going to map some way so that every single value, initial value, is only used once as the final value of the array. Is that okay? And the mapping is really not mapping the values, which are the case, to the array. It is just mapping the indexes. So by mapping the indexes, I can now establish and say that, okay, every single value that was in the initial value is now used in the final state of the array. Are we doing okay so far? Now, these cases they do not have to be unique. In other words, you can have an array like 5, 2, 5, 9. Okay, so 5 is appearing twice. Okay, it's okay because if you have 5, 2, 5, 9, then obviously this mapping is not going to work unless it is a freak accident that it does work. No, it does not work. Okay, so in this case there are 2 mappings that can make it work. The first mapping is 2 has to go here, 1 5 has to go here, the other 5 has to go here, and the 9 has to go here. So that is one function f that meets the requirement. Yep.
You said that's one function.
That is one function.
To confirm, that means the function we have up there does not actually tell us where each k is actually going to map. It just tells us that each k maps exactly once.
Yes, because it doesn't have to be unique. There can be multiple mapping that can still meet all of these requirements. So I'm going to use a red pen to indicate what the alternative is. Now, this one has no alternative because it is the smallest element. And this one has no alternative because it is the largest element. But the other two are non-unique. They are duplicates. So in the second mapping, I can map 0 to 2 and map 2 to 1. That would work as well. So we do have alternatives. But when you look at the statement of what a sorting algorithm needs to do, is we only need to find at least one mapping. And this is at least one because we got 2, right? 2 is at least 1, so it meets the requirement. So are there any questions about this particular application of a function? It is really just a tool, as a vocabulary to express, what does it mean to have an in-place sorting algorithm. Now, what is the big deal of going through all this mumbo jumbo to state what is the correct outcome of an in-place sorting algorithm? What is the big deal? Why do we care? Well, we care because I need to pass this class to get my transfer degree. Well, what else? I understand the importance of that. Okay, trust me, I do. I was a student once. But what else? Why do we need to know?
You have to define what the algorithm does mathematically.
And that will lend itself to, you're getting there, you're getting there.
So that you can prove whether or not it's actually right.
Exactly, okay? Being able to express the correct outcome of an algorithm mathematically opens up the avenue to prove the correctness of an algorithm mathematically. Okay, that is the importance. So that's the first part of this slide. Okay, and there's a second part to it too. And the scroll bar is not working out the way it's supposed to. It's all the way down here, so I can only scroll when I'm all the way at the bottom. Okay, so the second one has to do with the result of an assignment operation. And for those of you who took cisp440 from me, this will be stuff that you know already. Okay, this is just going to be a quick review of one of the things that we talked about in that class. If you have not taken cisp440 from me, this may be a new thing, but it is useful nonetheless. Okay, so I'm not going to go through the whole enchilada of how to prove or how to derive statements from one step to another step of an algorithm. All I'm going to do is to give you one example, okay? And I'm going to use the mouse pad here because I can certainly do that. So it'll be recorded. And what I'll do is I'm going to show you a particular line of an algorithm. So let's say on line 67, we have an assignment statement. Do you guys want me to use pseudocode representation, or do you want me to use C representation? I can choose either one. C? Okay, fine. No Python? Frankly, I don't really know how to write Python code. I can read Python code, but I cannot write Python code. Because to me, the lack of curly braces, or a clear indication of the beginning of a block and a clear indication of the end of a block just kind of bothers me. Because I've been using C, C++-ish language for a long time. Because JavaScript is like that, PHP is like that, Perl is like that, and Python is the only one that is not like that. But some people like Python because of that. Okay, so we'll go ahead and talk about one little statement here. It's not even going to be a very tricky one. So I'm going to say x gets x plus 5. Okay, fine. So here's a statement, and I know most of you are thinking, Tech, you should have known that you can use x plus equal to 5 to do the same thing. Yes, I could have, but this works too. And this works really well because I can now turn the right-hand side into a function of f. Okay, so we'll talk about this. All right. So in addition to this, I'm just going to use pre-67 to indicate a precondition of line 67. Now, when I talk about a precondition, I am not really talking about in a particular trace, in a particular instance of executing this particular algorithm, this happens, okay? A precondition of a particular line in program verification simply means every single time. I don't really care what the input looks like. I don't care how you run the algorithm. But if you are about to execute line 67, these conditions must be true. Okay, so that's a precondition that is regardless of the actual run of the algorithm. It's not a trace. It does not describe a trace. It describes universally. If you are about to execute line 67, this has to be true. Are we doing okay so far with that claim?
Yes.
Okay. Now, if I don't know any single thing about anything at this point, the simplest thing you can say is just true. Okay. But I don't want it to be like that boring, so I'm going to start with something. So we'll just say that for whatever reason, don't ask me why. Okay, because this is from derivation of all the lines that precedes line 67. So at this point, I'm not going to explain why I know x is less than z has to be true. I also know something else. I know x is greater than, say, 2 times y. And I also know that w is greater than z. Okay, these are the things that I do know. And there are no particular reason, just by looking at line 67, why these particular conditions are true. It's just true because of lines 1 all the way up to line 66. Is that okay so far? The second thing is, okay, but what is x? What is the value of x? What is the value of z? What is the value of y? What is the value of w? I don't know either, okay? This is a statement that has to be true if you're about to execute line 67. This has to be true, and it is the result of proving the behavior of all the statements prior to line 67. Is that okay? Now the question is, what can I say about post 67? In other words, if these things must be true before line 67, and I'm about to execute line 67, after I execute line 67, what can I say? Well, one thing I can say is x is 5 more than what it was, right? But how does it relate to all of the other variables? Go ahead.
X is still greater than 2 times 1.
But I can do a little better. Okay? So let's think about how we can do a little better. Now, when I express post 67, I'm referring to the value of x right after line 67 executes. So I'm not referring to the value of x before line 67. Okay, is that okay so far? So in pre-67, x refers to the value of x prior to the execution of line 67. In post-67, if I mention x at all, it will be referring to the value of x right after line 67 executes. I'll have you, and then you read next. Go ahead.
I'm going to say we could possibly know that x is still less than z plus 5.
Okay. That's true. Okay, go
I
ahead.
was going to say the same thing with x minus 5 is less than z.
Yep. Okay, so you're both correct, because they're the same thing, but you're both correct that you can make a strong statement and say that x minus 5 is less than z as a post condition, or as you said, x is less than z plus 5, okay, because they're equivalent statements. So I'm just going to write it down first, and then you guys can tell me, does it make any sense? Okay, x minus 5 is less than z, and x minus 5 is greater than 2 times pi. And nothing really affects the relationship between w and z. Okay. Is that making any sense to you? Okay, because in post 67, x is really referring to the value of variable x after line 67 executes. Is that making any sense? Okay. So if I have a general function on the right-hand side of the equal symbol of the assignment statement, what can I do in general? Because a plus 5 minus 5, we obviously know how that works, right? division and multiplication works out the same way. But what if it is really general? How can I do something about this when what is the general approach of doing this? In other words, I'm just going to say this is line n. Okay, I don't even tell you which line it is, and it's an assignment statement. X equals to f of x. That is all I'm going to give you. Okay, so in general, we can look at the right-hand side of an assignment as a function of the variable that is being changed. Now, if it does not involve the variable on the left-hand side, I can still look at it as a function, right? Because I can define stupid functions like this. I can define f of x to be 5. It's still a function. It is still mapping everything in the domain to something in the codomain. Now, this function is not injective, right? Because in order for a function to be injective, no two elements of the domain can map to the same element in the codomain. In this case, it's the extreme case of the other side. It is the extreme non-injective. Does that make sense? Because it maps everything to the same element on the other side. But is it a function? Sure, it's a function. You can give it any x, and it'll give you 5. Is that okay? So that means I can use f of x on the right-hand side of the assignment. Doesn't matter what it is, because I can always claim that is the function. Is that okay? All right. So in general, if this is the case, and we have a pre-line 67, pre-n, sorry. So in this case, I use n as a line number, and we'll just say that it is something. It is a statement consisting with conjunction, comparisons, and all kinds of cool stuff like that. Okay. The question is, in this really general case, how can I express the post condition? That really is the question. Okay. What is the approach? How do we come up with a way so that we can express post n, the post condition of line n, and hopefully we can reuse some portion of pre-n. Okay? That is the question. Okay, so now we have two possible cases. One possible case is f of x is not reversible. The other case is when f of x is reversible. It makes a big difference. Okay? So let me show you why it makes a big difference. So let's say we have a particular line. Okay, I'm gonna write it on the mouse pad just so that it's easy for everybody to see and it can be recorded. So I'll give you a second example. So let's say on line 133, okay, x gets a value of 20. Okay, so this time the right-hand side does not involve the same variable as on the left-hand side. Okay, now that makes it very special. Because in this case, if I can say that pre-line 133 is x is greater than z, okay, and I'm just randomly picking up using something here. W is less than or equal to 2 times x here. What can I say about the post condition of line 133? Yep, go ahead.
Z is greater than 20? Or Z?
We don't know. We do not know the value of x prior to the assignment. Okay? We just know the relationship between x and z, as well as between x and w prior to the assignment statement. In other words, I have no idea what is the value of x, or the value of w, or the value of z. I just know how they relate. But the assignment statement is just changing x to 20. It's like, okay, from here on, it is 20. Now, how would that impact the relationship between x and the other variables? I have no idea. Without knowing the actual value of x before the statement, I cannot make any of these claims. So in this case, I really cannot reuse anything from the precondition. The only thing I can say is, oh, well, you know what? The only thing we know after the assignment is x equals to 20. Because x is greater than z may not be true anymore. Right? Because what if z had a value of what if x had a value of, an example here. So what if z had a value of 30, x had a value of 31? Well, now x is no longer greater than z, right? What if what if w, you can basically make arrangements, where a condition that was true before based on specific values is no longer true after the assignment. So that means I cannot make those claims anymore. The only thing I can be sure about after the assignment is x has to be 20. That's the only thing I know. Does that make any sense? But what is making this particular assignment statement so damaging that I cannot reuse any knowledge or any relationship between x and the other variables? Whereas in the other case, it seems like maybe we can keep most of it. It's overwritten in a way that is
Not preserving the variable.
that is not reversible. That is not reversible. In other words, just by looking at x being 20 after line 33 does not give me any way to reverse the operation and say, oh, you know what? Knowing that x is 20 after line 133, I know that x has to be x, y, z, or whatever value before line 133. That ability is gone because the function is not
Reversible.
It's not reversible. And it's not reversible because it is not bijective. Is that making any sense? Because if you map all values from whatever to 5, knowing it is 5 doesn't give you any ability to reverse it. Whereas before, x plus 5 is wholly reversible. Okay, let's take a look at x plus 5 then. Okay, so if the right-hand side is x plus 5, what makes you think this is injective? In other words, if I change the value of x, it will change the value of x plus 5.
The domain only maps to unique elements in the code domain.
It maps exactly. Okay, because you can prove it by contradiction. You can basically say, if you map two different values to x plus 5 to the same value in the code domain, okay, then what happens to that value minus 5? It has to have to only one of the two that you start off with, right? But you've got two different values to start off with, so that doesn't make any sense. Is this also surjective? Now that we know it's injective, is it surjective too? In other words, if I give you anything that's the result of f of x, can you reverse it back to the original x? And how do you do it? What is the magic to do that? Minus 5, exactly. So f inverse is just x minus 5. And it is because of the existence of an inverse function that we can now reverse the operation. So getting back to what we are talking about here, so that means in certain conditions we can reuse a lot of the precondition. But the thing is, if f is injective and surjective, then we can make the following claim. So this part is, a little bit, I'll explain it later. Okay, so I'm gonna type it first, then I'll explain it. So x with f inverse to x. Okay, so this is a substitution function. It's just like with an editor. With substitution, there are three components. The first component, which is pre-n, is telling you, okay, what is the original? Okay, give me the original. Because when you perform substitution on anything, you're working on, something, right? Within this document, within this text, find the following. What is the following? It's x. In other words, locate all occurrences of x in the precondition of line n. But as the name substitution implies, we are substituting x, whatever we're trying to find, with something else. What are we substituting x with? The inverse function of f applied to x. That is what we are substituting x with. And then we can preserve just about everything in the precondition. Are we doing okay so far with this really general form of going from the precondition of an assignment statement to the post condition of an assignment statement. Is that okay so far? Okay. And this is important because the most important, the most useful and elemental statement in any programming language are the assignment statements. Without assignment statements, programs do not do anything because they're not changing anything, right? They can make decisions, you can make conclusions, but you cannot, actually change anything or to do any real processing. The assignment to something like this, okay, x equals to 0. These happen in programs. Obviously, they are very important as well because they are the initialization type of statement. They make sure that at the beginning of a loop, your counter starts with a particular value. Okay? So they're very important, but they are not as frequent as x gets x plus 1, the other type of assignments. These typically happen at the very beginning of a loop or the very beginning of a program, but x gets x plus 1, x gets x times 2, that sort of thing happens in between, which means these things, even though you can lose all the information before, they're not really a big deal because we don't have a whole lot of stuff to say before this. Are we still doing okay so far with what we're talking about here?
So post conditions become the next statement's preconditions. Yeah.
That is correct.
What would something like post of x plus f of x actually yield when you go to make it into a precondition for something else?
Could you repeat that question, please?
So you get the substatement and everything in there. What does that evaluate to when you turn that substatement into a precondition for the next line of code?
Let's go ahead and take a look at some examples. Okay, so we are, I'm repeating a little bit of the material from my own CISP, 300. So some of you may feel a little bit bored because we talked about this stuff, already. But this is in a different context, so it's kind of, important as well to talk about it here. So what I'm going to do next is to give you a, real kind of run of, what we are doing here. So we'll start with line 1. Line 1 is x gets a value of 0. Line 2 is x gets x plus 1. Line 3 is y gets x. Line 4 is y gets 2 times y. And that's it, okay? So I only have 4 lines of code. And obviously, all of you, because you're now in this class, just from visually going through the code, you can figure out the answer, what is going to be in x and what is going to be in y. Is that okay so far? Okay. So to make this a little bit more fun, I'm going to change this to a k, and many of you can substitute k and come up with an equation and say, okay, x is going to relating to k this way at the end, and y is going to related to k this way at the end. But that's okay. That's not really the point. Okay, I'm not tracing this code. What I'm doing is I am working out the post condition of the entire sequence of statements. I have to claim something about the precondition of the very first line. So unless this particular algorithm has any type of assumption to make prior to line 1, the only thing I can really claim before line 1 is true. Okay, because true is the most general statement that is in general true. Okay, so that's the only thing I can claim. When we go to line 1, okay, I want to derive what is the post condition of line 1. So without going through all the substitution versus forget rule and stuff like that, you probably can tell that the only thing we can tell is x equals to k as a result. Now in this case, because I'm not using pseudocode where I typically use a left arrow to indicate assignment, you have to make sure that you understand in the condition. Let me just emphasize it here. This is saying x equals to k. Maybe I should just use double equal to be consistent with the C syntax. Okay, so this is an equality, not an assignment. You do not put an assignment where a condition is expected in this case. Okay. All right. So pre2 is the same as post1 because those two statements are sequential, right? So I can just basically reclaim that x equals to k right before line 2 executes. Now on line 2, on line 2, f of x is x plus 1, so f inverse of x is x minus 1. Is that okay so far? It's not enough to know that the inverse function exists. You have to know what it is, because we have to apply that in the substitution operation. So knowing that we have an inverse function and the inverse function is just x minus 1, this is what we'll do. We say post 2, the post condition of line 2, right after line 2 executes, the following has to be true. Okay? And the general form is, it is the result of a substitution operation. What we start off with is the precondition of line 2. What we really care about are the occurrences of x, which is the variable on the left-hand side of the assignment. And what we'll use to change it is f inverse applied to x. Do you remember this general description? Okay. So now we'll go ahead and expand every single component inside the substitution operation and figure out what it would look like. What is pre2? Well, pre2 is just x equals to k. X is x, not a big deal. F inverse applied to x is x minus 1. Do we have any questions at this point? This step is just expanding all the terms from the previous step. In other words, oh, do we know what is pre2? Sure, pre2 is x equals to k, that's from before. X is x, doesn't need to be explained there. F inverse is something minus 1. So f inverse applied to x is x minus 1. So now we have all the ingredients. Then the next thing we do is to actually go ahead and perform the substitution operation. The substitution operation is nothing more than what you already understand as find and replace with any word processor. This is all it's going to do, is to find and replace x with x minus 1 within everything in the precondition. That's all it's going to do. So the result of that is x minus 1, which is taking the place of x, equals to k. That's the conclusion. That is my post 2. Is that making any sense? If I know that x equals to k before I add 1 to x, after I add 1 to x, what can I claim? X, well, we typically say x equals to k plus 1, but this works too, right? X minus 1 equals k is saying the same thing. It's all working out, right?
So could you, in fact, at this point, just move the minus 1 to the right side and make it plus 1? So
Absolutely, but it doesn't buy us anything, so I'm not going to do it.
Okay.
Yeah. If it does buy you something, then yeah, go ahead and do it. Because the most important part is to establish how x relates to other terms. And if I have this relationship, it's fine. Okay? But if you want to rewrite it as x equals to k plus 1, that's fine too. Yeah. All right, so let's move on to the next line. Okay, pre3, which is the line right next to line 2, is post 2 because those two statements are sequential. Now, these two statements are sequential not necessarily because they're right next to each other. It is just because of the flow of the program. In other words, if you have conditional statements or loops of some kind, just because one line or one statement is after, in terms of line number of some other statement, does not mean they have to be sequential. Okay? But in this case, we just have a single sequence, so they have to be sequential. And I'm just going to repeat what we had earlier, which is x minus 1 equals k, like that. So now we have to derive what is post 3. I'm not going to go through the forget rule application, because this is not the right time to do it. Okay, the first question is, if I know x minus 1 equals to k prior to this particular statement here, do I have to erase anything that I know about x? Because is the statement changing x in any way? Nope, it's changing some other variable, right? So whatever we knew about x, as long as it does not involve y, hey, we can keep that. So that means we can keep the fact that x minus 1 equals k. Okay, x minus 1 equals k is in fact, hey, we're still good with this. But in addition to this, we also know one thing now. We also know that y and x are the same, because that is the effect of that particular assignment statement on line 3. Are we still doing okay so far? Okay. Now typically at this time, if k is a constant of any kind, I would also go one step further and say y equals to k plus 1. Okay. In other words, I want to reduce the dependency between variables. I want to resolve as much stuff and connect them to actual constants as much as possible. Okay. So if k is a constant, in other words, k is not a variable, I would take this one more step and go x minus 1 equals k, and y equals to k plus 1. Okay. Okay, so we're almost done. Now we work with pre-4, which is post 3, because these two are sequential. And just to restate what it is, I'm just copying and pasting it here. Now we want to derive what is post 4, right? Okay, now post 4 is going to use the same rule as in post 2, because on line 4, okay, f of y in this case, which is whatever is on the right hand side, is 2 times y. Okay, is that injective? When I have f of y being defined to be 2y, is this injective? Does it map different elements of the domain to different elements in the codomain?
Yes.
Okay, it is injective. If y is a real number, okay, so we'll just consider real numbers here. If y is a real number, is it surjective?
No.
Yes.
Yes, it is.
No.
No.
Yes.
It is surjective. If y is a real number, it is surjective. Now, if y is an integer, it is not surjective. Okay, because if you have an odd number, it does not. It doesn't map to the odd numbers if it is in. We're only dealing with integers. But if we're dealing with real numbers, then it is surjective, because given any y as a result, you can divide it by 2 to get back to the original value. So in this case, we do have an inverse function of y, and that is just y divided by 2. That's the inverse function. Kind of makes sense, if you multiply something by a constant, to undo that, you divide it by the same constant. Is that okay so far? Okay. So if that is the case, I'm going to write it in the whiteboard too. So in this case, we do have an inverse function of y, which is y divided by 2. Oops, y divided by 2, like that. So that means we can use the substitution operation again. So the post condition of line 4 is applying the substitution operation, and we'll use pre-4 as the basis. This is where we start off with. We'll look for all occurrences of y, which is the variable on the left-hand side. This is the variable getting changed. And we'll replace it with f minus 1, which is the inverse function of f, applied to y in this case. It's not x anymore because y is the variable on the left-hand side. And then in the next step, we just expand out all the terms. Pre-4 is this mess here, so we'll just copy and paste the entire mess into the substitution, the first part of the substitution operation. Y is y, no big deal. And then the inverse function of y is y. The inverse function of f applied to y is y divided by 2. So that is the actual replacement. And in the next step, we perform the actual substitution. Now, when we perform the actual substitution, you kind of just, it really is just looking for y and replace every single y with y divided by 2. The first comparison does not involve y at all, okay? So we're not going to touch it. Leave it alone. The second one does involve y, so we'll change this y to y divided by 2. That's it. Now, obviously, you can rewrite that as y equals to 2k plus 2. Okay? That's the same thing, but it doesn't change the relationship. This is how we go step by step and use the substitution operation in order to derive the post condition of an assignment statement from its precondition. Are we doing okay? All right. So this is, for those of you who took CISP 300 from me and was thinking, oh man, why do we have to deal with pre and post conditions? Well, this is why we are dealing with pre and post conditions, is because we can go step by step, go from the initial state of a algorithm and come up with the final state of an algorithm mathematically. Okay. And obviously, if someone got a thinking, oh, well, thank you, because that's a good reminder. I'll take it as a reminder to take roll. Thank you. Not to encourage it, but for this particular instance, it's helpful. Yep.
You say mathematically, but to me, everything becomes so far is just logic.
It is logic. Logic and math are really the same thing. Logic is one branch of math, and computer science should have been considered a branch of math as well, and not call it a science. It's really just computational branch of mathematics. It's not a science. There's nothing about computer science that is a science. What is a science? Tell me what is a science. Don't tell me psychology.
Recording data.
Exactly, and give me an example. Physics.
Physics or chemistry.
Physics, chemistry, biology, astronomy, those are all sciences because you are out there discovering patterns, laws.
Things that have already been made. Things that already exist.
Things that are already in existence, and you're just trying to figure out, okay, how do I model this, right? Okay, this is weird, but I want to find a way to model. So that's science. And you want to have a way to repeatable experiments. Okay, you want to be able to observe the outcome of experiments so that you can compare hypotheses, right? You can come up with, okay, I have a hypothesis like this. How do we know whether it's true or not? Can we design an experiment that is repeatable and has observable outcome that can either qualify and say this hypothesis is, I cannot prove it wrong, or I can prove it wrong. And computer science has none of those characteristics, right?
They have some, don't they? Like artificial intelligence and like quantum computing, trying to discover other things.
With AI, it is a branch of what we call cognitive science, which is a branch in psychology. Okay, because we're trying to model how the neurons work individually and also collectively. Okay, but it's not really computer science itself. If you look at computer science, what Turing did was truly computer science. And what was it? It's all math, right? We make up all the rules. We make up all the laws. We make up all the operators. We make up all the syntax. And now we say, okay, let's see how that works. But it's not based on natural, phenomena. So that's why computer science really does not have a science component to it, but it does have a math component to it, because that's what math really is. Yep.
So on post 4, is there any reason we didn't include like 2y over 2 equals x as opposed? Because that's not technically
because E is a constant, and as I said a little bit earlier, if I have a chance to decouple variables from each other, I would, because that really makes it stronger, and it makes subsequent changes to x not to affect y anymore. Because when you have two independent variables, x and y in this case, and we'll just assume the k is a constant, you want to reduce the dependency of the variables. You don't want to, if it's possible, you don't want a variable to be expressed in relationship with another variable. You want to tie it down to a constant if it is possible. So in this case, it was possible, and so we tied it down to a constant, which is k.
Would that be an incorrect answer?
It would not be an incorrect answer, but if you tie it to x, if later on we assign a value into x, it will also invalidate what we do about y, and that's why we don't want to do that. And to illustrate that point, let me just go one more step, make a line 5 of this one, and that will really prove the point that I'm trying to make. So I'm just going back to this code here, and we'll make a line 5. So line 5 is just reinitializing x to 0. That's all. Okay? Which doesn't seem to do a whole lot of stuff, right? But let's see how this is going to impact the post conditions. Now, it doesn't do anything to the stuff that we have already derived. Okay, that's fine. But when you look at pre-5, okay, pre-5 is easy because it's just post 4 because these two statements are next to each other. But what happens about post 5? Okay. Now, when you look at post 5, obviously the first part of the conjunction, gone. Because we knew before x get be set to 0, that x is k plus 1. Well, that is probably not true anymore, right? Unless k is -1, right? And so there's always that chance, but if there's a possibility that it cannot be true at this point, you have to take it out. So we have to take out the first part. And what about the second part? Y divided by 2 is k plus 1. Do we have to take this part out?
No.
Does it mention does it mention x whatsoever? It does not. But it's not mentioning x only because earlier we converted x to k plus 1 when we had a chance. Is that okay so far? So that's why we kind of did this conversion here, just so that later on when we change x, it does not erase something that we know about y that really has nothing to do with x anymore. But to finish this one, I still have one more little thing to say, because from here on we know that x is in fact 0. All right. Are there any questions about all this stuff here? How we can basically make statements about lines of a particular algorithm? Well, I have a question. See, I'm the one who asks most of the questions, not you guys. There are 50 of you versus 1 of me. And I'm the one who's asking questions. Okay, I have a question. This is a stupid program. Well, it's not a question, it's a statement, right? It's a comment. This is a stupid program, okay? It doesn't have any branches, doesn't have any loops, doesn't have any subroutines. So it's useless to be able to do all this stuff, but only to a sequence of statements only involving assignment statements, right? But what about loops? What about conditional statements? All the important stuff in programming. Well, unfortunately, that is not in the curriculum description of this class, because otherwise I would love to talk about that stuff, okay? How do you analyze an algorithm that has conditional statements, okay? How do you derive the post condition of a conditional statement that has a then branch and a else branch, okay? I would love to talk about loops too, okay? Loops are kind of tricky, but in this class, because we'll be talking about proof by induction, we don't have to deal with loops anymore. Okay? How do you get rid of loops? Well, first of all, are there any programming languages that do not have loops as a construct, as a syntax? There are several, okay? Well, assembly is one, but it's not, it's not in the right context. Lisp, okay, L-I-S-P as a programming language has no loops. There are no for loops, while loops, or do while loops, okay? No pre-checking or post-checking loops. So how do we do something repetitively? What is the other way to do repetition in your C, C++ programming classes?
Recursion.
Recursion, that's right, okay? So there are theory, not theory, but there are people have proven recursion is just as expressive as loops. They're equivalent, in fact, okay? In other words, if you can express an algorithm using loops, you can re-express the same algorithm without loops, but make use of recursion. Yep.
How do you transform a recursive function to a
Non-recursive to iterative, what we call iterative. Okay, so let me finish the earlier statement, then I'll address that question. Okay, but it also goes in the opposite direction. In other words, if you give me any recursive algorithm, which is what you just mentioned, you can turn it into a non-recursive function using iterative statements, loops, basically. Okay, and the way to do that is to maintain your own stack. So you have to use a specific, explicit array, at least one, depending on how much stuff needs to be tracked. But you need to have your own quote-unquote stack implementation. It's usually in the form of an array, or if you program in C++, it also has a template class for stacks. So you have to implement your own stack, but you can turn any recursive subroutine into non-recursive. The non-recursive version is going to be messy, depending on how many recursive or recursion points you have in the original algorithm. So for Fibonacci, it's going to be quite messy because you have 2 points of recursion. For factorial, it's easy because you only got a tail end recursion where the recursion only happens at the end of the entire algorithm. That makes a very clean way to convert back into iterative subroutine. But if you have multiple recursion points then it gets quite messy. Or if the recursion is in the middle, it also makes it kind of messy. So in this class, we will investigate, recursion or the relationship between recursive subroutines and proof by induction, because those two things, kind of go hand in hand. They're very related. All right. So this is a fairly long discussion of why functions or the studying of functions is important, because now, if we know that f of x is reversible, we can have a way to relate what we knew about the variables to the next statement, which is really helpful because we can now step by step, prove an algorithm is actually correct. Are there any questions about this part? What is the consequence, since we're talking about proving an algorithm is correct mathematically? So what is the consequence of not doing that? Yep. We get bugs. We are suffering every single day because of that, right? And today is Patch Tuesday again. So why do we have patches or fixes, to software? It's because well, when software is released, nobody actually verified it is 100% correct. People throw test cases at programs and say, well, since all the darts land on blue spots, the program is okay, we can release it now. Of course, end users have special magical powers to make the darts land on red dots instead of blue dots, right? Yep.
I was just wondering, if it's actually practical. I mean, with what we do in here are very simple statements, and it takes a lot more time to prove a statement that you can write in a few seconds. So, is it actually practical to prove some huge complex?
That is a very good question. So let me repeat the question just in case people over there cannot hear you. So the question is it practical to use mathematical proofs to go step by step to show the result of a particular algorithm? The answer is it is not practical with the computation power that we have now, but if Moore's law is keeping up, or if we have a breakthrough with different types of computation hardware, who knows when it becomes actually practical. The reason why I mentioned that is because a lot of algorithms, a lot of ways of doing things was not practical before. Okay, let's think about automated drones, okay, which we already have. Okay, the military is definitely experimenting with automated drones. Okay, so think about the practicality of an automated drone that is basically flown by a computer. Okay? Today it's perfectly practical. You can go ahead and buy a $400, $300, remote control airplane from Harbor Freight, no less. Okay, so you can afford to crash a few if you want to, and then attach a Arduino to it, a GPS unit, and then you can program that thing, right? Now, whether you can program it to make it actually useful to do something is a whole different story, but it is programmable. Okay, it will cost you, how much is a GPS unit that can attach to an Arduino?
Like a small one?
Yeah, well, it has to be kind of small and light. So let's call that what, 50 bucks?
Yeah.
Okay, and Arduino is about what, 20, 30 bucks? Okay, let's call it 100 for just the electronics.
The
Okay?
Uno? Like the Arduino Uno or something like that, it's like 50.
50?
What is
So,
that? You're saying
Arduino?
Yeah, is that a programming unit or?
It's a cool
small-
thing that you guys
It's a small developer board.
Okay, so it's like a Raspberry Pi.
Arduino. Okay. So an Arduino, if you look at images, is basically a single board computer that is kind of small, but they could have made it smaller by using smaller components.
Is it like the Raspberry Pi?
It's kind of like a really small Raspberry Pi.
Oh, really small?
Yeah, but it doesn't run Linux. Okay, so it has no operating system on it, but it does run C code, so you can write programs in C and C++ to program these things. So the bottom line is it is programmable. Okay, it is programmable in C and C++. So we can also attach these things and hook it up to like a GPS, level sensors, accelerometers, and stuff like that. So in other words, the whole point is, well, you can probably throw something together for less than $1,000, and it has the ability to control its own flight. Okay? So it is practical today. Okay? both from the perspective of how much money you have to spend, whether the technology is there or not, and so on and so forth. Okay. What about at the end of World War II? Would it be practical? Okay. And I'm not even talking about airplanes. Okay. Let's just use propeller planes. Okay, fine. I mean, those things have been in existence since what, World War I?
To control its own
Biplanes. But how do you put a computer on an airplane at the end of World War II? Have you guys watched the Imitation Game?
You get a C-130, and then you pack the entire cargo bay full of tubes.
And then you need another C-130 to carry the generator,
Right.
and have those two airplanes to be tethered so that one is a generator to supply power to the other one, but the control signal has to go back and forth so the two airplanes can fly in tether and kind of fly in a formation.
But then the limitation of them controlling their own flight, there were no GPS satellites up in the space in 1945.
That they can fix with inertia guidance. Okay, because for the longest time, they used inertia guidance system. Even the SR-71 used non-GPS technology, because that's back in the late 60s, 70s, or something like that. But that's prior to GPS, and they used inertia guidance as well as observing stars to figure out the heading and the location of the airplane with high precision too.
Yeah, but like when someone's back there with a slide rule inputting stuff into the data and you're starting crashing into the ground, it can be kind of difficult to make sure you control your own flight.
Right, that's true. But getting back to the question, whether it's practical or not, this big digression has to do with that, right? Because back then, even when someone proposed and say, hey, we got computers and we got airplanes, we can have a computer to fly an airplane. Well, somebody can come up with that idea, but it's not practical because you cannot put a computer on an airplane. Okay, but with the speed of progress of technology for computers, it's now possible, right? It's not just possible; you can do it. Okay, a student club. Oh, Danny's not here, but if anyone is going to the student club like today,
I qualify.
you can mention it to him and say, we want to build an autonomous drone just to prove it is possible. But the practicality has a lot to do with how much processing power we have, and we have no idea, when we'll get to that point. But the way things are going, we can maybe one day have that much processing power. So maybe it's not practical today, and certainly it was not practical when it's called program verification. That's the formal name of that kind of study. It's definitely not practical back in the 60s and 70s when people were really going gung-ho and saying, okay, we want to have this. That's why Prolog was invented as a programming language. But there's no telling when it will become actually practical. So that was a good question, but a lot of stuff is, cannot be predicted. I know I'm going to digress here. Once I go in a digression, I keep going. And yesterday I was talking with my son, and he was reading Ender's Game. Okay, so think about Ender's Game. The original story was published in Analog, a science fiction, magazine, in fragments, in 1977. And the book was put together and published, I think, in 1985. Okay. And back then, I don't think they would have any idea of, being able to do simulation the way they depicted it in the movie. How many people watched that movie? Kind of, okay. But they definitely made use of, simulation, drones and all kinds of stuff that we today think, okay, that's probably possible in the near future. But the story was written in 1977. Okay, and a lot of the concepts are now saying, hey, it actually can be done. Technically speaking, the technology stuff is kind of there. Okay, so that means we are actually, technology is progressing so fast these days, it is almost outpacing science fiction. Really, kind of think about it. Yeah. Knight Rider. Okay, many of you are way too young to have watched the original Knight Rider. Okay.
Voice-controlled cars?
Knight Rider was a Trans Am, Pontiac Trans Am that is kind of souped up with like the sweeping eye. I call those Cylon eyes. Okay, with the Cylon eyes in the front and the main character, what was his name? Michael.
Michael and Kit.
Yeah, Michael Kidd was able to communicate with his car on his watch, which is really clunky, okay? And he can say, hey, Kid, come around the corner and pick me up, okay? You can do that now. All Teslas can do it now. Now, what Knight Rider did not anticipate was the electric cars. Knight Rider was a dyno fuel burner. It was not an electric car. And now we are actually getting past science fiction. And how long was that ago? What was the year when they came up with Knight Rider?
83.
The early 80s?
Yeah.
Okay, that sounds about right. And now we are already surpassing, science fiction, even though it's popular science fiction, in the 80s. So getting back to, what you also talked about earlier, it's like, well, maybe it will become possible one day.
So we have to worry about HAL then?
HAL 9000?
Yeah.
Worry about Skynet before I worry about HAL.
If Skynet is running on Microsoft platform,
Oh, then I wouldn't be
worry
worried
about
about
it
it.
because it will be too busy patching itself. Okay, I want to kill you. Hold on. I'm downloading a patch right now. I'm going to kill you in 30 seconds after I reboot.
And now we all see tax disdain for Microsoft.
Yep.
I'm afraid I can't do that, Dave.
What?
I'm afraid I can't do that, Dave.
Yeah, from 2001, I'm surprised that you guys actually watched that movie too, because to most people it's really boring, like traveling in
It is
outer space
slow.
is silent. It's like, really? Silent? But that's not the impression I get from Star Wars.
If you have the Blu-ray for that, it looks amazing on
Right.
a big TV. The Blu-ray for 2001.
Oh.
It's been they did like a whole remaster. They have like the practical effects and everything.
So they remastered everything.
Yeah, and it's like
Science fiction.
You like never see special effects.
You basically make yourself aware and the
I'll keep an eye on
astronauts.
All right. Well, we're running out of time today. I'll see you guys on Thursday, and don't forget about the homework assignment. Right. So this is cool. I managed to digress and still